Have you ever heard of the term quantum entanglement? It's everywhere in the news these days, but do we really know what it means? There are two parts to this episode. First, we will go over the science behind entanglement, and second, we will discuss how the spooky action at a distance can be used to build a new type of internet that could connect us faster than light. This is our digital channel. Quantum mechanics is a theory about the physical world. Like any scientific theory, it uses mathematics to describe nature. But unlike classical physics, quantum mechanics has some very weird features. Let's again consider two entangled electrons, each of which can be in one of the states, S up or S down. This is why physicists don't talk about entanglement as a resource for communication. However, entanglement is a valuable resource for computation. Physicists call it quantum information. In fact, it's this quantum information that is being used in quantum computers to outperform conventional computers. It was published in Nature in 1998. In their experiment, they teleported the spin state of a single electron from one location to another. Another method is quantum networking, which is based on the idea of connecting distant quantum computers by quantum links. In their experiment, they connected to single photon sources with an optical fiber. The photons emitted from the two sources were entangled, so that the quantum state of the photons was correlated with each other. This allowed them to teleport the quantum state of one photon from one location to the other. It's a beginner's course that covers the basics of quantum mechanics and quantum information. These links can be established by sending photons through optical fibers. There is also a third method, which is based on the idea of creating a wormhole. A wormhole is a theoretical object in general relativity that connects to distant locations in space-time. This means that information can be sent from one location to the other by first putting it into a wormhole, and then extracting it at the other end. The nice thing about this method is that it doesn't require moving any physical objects, not even photons. But unfortunately, we have no evidence that wormholes actually exist. And even if they do exist, it's unclear whether we can control them well enough to use them for communication. The photons are entangled with the two ends of the fibers so that the quantum state of the photons is correlated with the quantum states of the two computers. This allows quantum information to be distributed between the two computers without moving any physical objects. A good thing about this method is that it can be used to connect multiple quantum computers to each other. This forms a network of quantum computers, which is why it's called quantum networking. This is quite remarkable because the spin state of an electron can be thought of as a qubit, the basic unit of quantum information. So they essentially teleported a qubit without moving any physical objects. The reason is that a quantum computer can be in many different states at once, whereas a conventional computer can only be in one state at a time. Quantum teleportation can be used to connect single qubits, whereas quantum networking can be used to connect quantum computers. Both methods have their advantages and disadvantages, but ultimately the best method will depend on the specific application. This means that a quantum computer can explore many different paths through a mathematical problem simultaneously, whereas a conventional computer explores only one path at a time. This is why quantum computers can solve certain problems much faster than conventional computers. The state of the combined system is described by the following mathematical expression. Well, one way to distribute quantum information is using quantum teleportation. This is a protocol that was first proposed by Sandu Popescu and Dorota Haronov in 1993. They were awarded the Nobel Prize for this discovery. In this protocol, quantum information is sent from one place to another by throwing away most of the information about the quantum state, and then using classical information to reconstruct the original state. To explain this, let's again consider a quantum state of two entangled electrons. This state can be moved to another location by sending one electron to each location. In this case, the quantum information is now located in the second location. But what about the first location? You might think that the quantum information has been destroyed there, but actually it hasn't. The quantum information is still present in the classical information that describes how the state vector can be reconstructed from the two electrons. In other words, quantum teleportation does not violate Einstein's theory of special relativity. It's just a clever way to hide quantum information in plain sight. It looks a bit complicated, but really it's just a vector with four components. The first component is the probability amplitude for the first electron to be in state S up, and the second to be in state S down. The second component is the probability amplitude for the first electron to be in state S up, and the second to be in state S up, and so on. Now, we can calculate the probability for each of these four cases. For example, the probability for the first electron to be in state S up and the second to be in state S down is the square of the absolute value of the first component. In this basis, the state vector describes all possible combinations of the two individual states. This representation of the state vector is called a product basis. The state vector of the unentangled particles would simply be a product of the individual state vectors. Then the state of the combined system would be in a direct sum of the individual states. Now if we make a measurement on the first electron, then we obtain the value S up with certainty. This means that the first component becomes real, while all other components become zero. But here's the crucial point. Even though the second electron is far away, the second component also becomes real. Therefore, the outcome of the measurement on the second electron is known before the measurement is done. But this is only true if we use a special type of measurement that leaves the state vector in the same basis. In other words, if we measure the spin of the second electron, we will find it to be S down. If we had chosen a different basis, then the second component wouldn't have become real. But the important thing to realize here is that the second component only becomes real after we have made a measurement on the first electron. Until then, it's just a complex number. Therefore, no information can have traveled faster than light. It is really only the correlations in the state vector that make it appear as if information is being transferred faster than light. This is why Einstein called entanglement spooky action at a distance. This is called a superposition. For example, an electron can spin both up and down simultaneously. This is not only because of the laws of nature, but also because time itself doesn't pass at places that move with the speed of light. Thus, there is no medium through which information can be transferred faster than light. Information is anything that helps you to distinguish between two different states of a system. In the example with the electron spins, the information is contained in the question, what is the spin state of the second electron? If we know that the first electron is spinning up, then we know the answer to this question. Therefore, information traveled from the first to the second electron instantaneously. But wait a minute, isn't that faster than light? How is that possible? Once we measure the electron, its wave function collapses, and we get one definite answer, either up or down. However, there are also cases when two or more quantum particles can exist in a combination of states. This is called an entanglement. For example, imagine two electrons, each of which can spin up or down. If we know that the first electron is spinning up, then the second electron must be spinning down, because they must have opposite spins. We say that the two electrons are entangled. If we now measure the spin of the first electron, then we immediately know the spin state of the second electron even if it's light years away. So entanglement is a correlation between quantum particles. But is this correlation faster than light? One of the most counterintuitive aspects of quantum mechanics is that tiny particles like electrons and photons can exist in multiple states at once. Before answering this question, let's take a look at Einstein's theory of special relativity. It tells us that nothing can travel faster than light. To understand what's going on, we need to look at the mathematics behind entanglement. So now you know that entanglement can't be used to send signals faster than light. But how does this relate to the new type of internet? An interesting side note is that the first experimental verification of quantum teleportation was done by the group of Sandu Popescu himself. Now, quantum teleportation is not the only way to distribute quantum information. The first experimental demonstration of a quantum network was done in 2009 by a group of researchers from the University of Science and Technology of China. However, quantum teleportation and quantum networking are not the only ways to distribute quantum information. So when it comes to distributing quantum information, quantum teleportation and quantum networking seem to be the most promising methods. If you want to learn more about quantum information, check out our course on Brilliant.org.